All right, Chapter 11, Part 2. Let's take a look at this example. Example number 1, balancing a meter stick. So a mass of 15 grams is placed at the 70 centimeter mark on a meter stick. The meter stick is supported at center of mass, which is located at 50 centimeter mark. Where must a 20-gram mass be placed in order for the system to be in equilibrium? So write down things that you have. Pause the video right now. Write down the things that you have and come back. Let's work on it together. So what we have is we have a meter stick, which is 1 meter or 100 centimeter. So what we have is this. Okay, and it is supported exactly at the center. So what I have is half of the L length over here and half of it over there. So we have a 15 gram is placed at 70 centimeter mark. So let's say that this is 50 at the center, okay? And then let's say that this is 70. So we have a mass of M, 15 grams right there. Where must a 20 gram be placed in order for the system to be at equilibrium? In other words, I have a 20 gram, let's say that this is M1. So M2 is 20 grams, but we don't know where we should put that. In other words, if we want to have the equilibrium, all the torques in all the directions should cancel out. So I have an mg or m1g down, okay, which is causing this system to rotate clockwise, okay. And then I have another mg, this time m2g, which is causing the system to rotate counterclockwise. So they should produce a torque, but the total torque, in order to have the equilibrium, the total torque should be 0. Okay? And we're talking about the rotational here at the same time. So, in other words, I have to have torque 1 plus torque 2 being equal to 0. If you add them up, you should get a 0. So, let's take a look. And I consider this to be the axis of rotation here. So I have a 20 centimeter here so this is 20 centimeter of length. So tau 1 is R cross F, okay, general format of it. I have R, F, sine of theta. In other words, in order to find tau 1, I have to multiply the amount of R1, which is 20 centimeter. I am not going to change that at the moment. I am not going to change the 20 centimeter to meters. I have to do it, but I'm not going to do it. I'm going to keep it as 20 here, so 20 centimeter. F is M1G, okay, down. And the sine of the angle between F and R, so this is R and this is F. The sine of this angle, which is sine of 90 degrees, okay? So torque 1 is 20. Let me actually use R1 here, just because I want to substitute the numbers later on. So let's keep it as it is. So I have R1, M1G sine of 90. In other words, tau 1 is R1 M1G, because this guy is just sine of 90 degrees is just 1. So tau 1 has this formula, M1 R1G, okay? Tau 2 would be the same, okay? So tau 2 would be R2 M2G, because if you're looking at this, it is the same thing, but this is causing a counterclockwise motion. So it has the same formula. Okay, now if you add them up, you have to get 0. The most important thing here is that one direction should be positive and the other direction should be negative. If we want to be consistent, the counterclockwise should be negative. The counterclockwise should be positive, and clockwise should be negative. So I have to have a negative here. Okay, I have to have a negative here in order to be consistent. So I am choosing a counterclockwise to be positive and clockwise to be negative. Okay, so I have a positive right there. So if you add them up, you have to get 0. Tau 1 plus tau 2 should be equal to 0. So negative R1 M1G plus R2 M2G should be equal to 0. We can factor out G and get rid of it. In other words, G times R2 M2 minus R1 M1 should be 0. And then this means that R2 M2 minus R1 M1 should be 0. And then this means that R2 M2 should be equal to R1 M1. Okay, now in order to find R2, which is this length, so this is R2, R2 would be equal to M1 R1 over M2. So R2 is M1, which is 15 grams. This is 20 centimeter, and M2 is 20 grams, correct? That is correct. So 15 gram, let me do this, 15 grams, okay, 20 grams, and then this is 20 centimeters, okay? So this gram and this gram will cancel out. This 20 and this 20 will cancel out. We have 15 centimeters left. So 15 centimeters is this R2, okay? So what you have is this is at the center. This is 20 centimeter as your R1, and this is 15 centimeters as your R2, and then you have a 20 grams of mass right there, and then you have a 15 grams of mass there. In other words, in our case, M1 over M2 should be equal to R2 over R1. Or in fact, that's the formula for equilibrium in our case. So I am going to put some stars around it because it is important. All right, so let's go to another example. Example number 2. Pause the video and read the problem. Write down the things that you have, and then let's work on it together. So what we have here is that the figure to the right shows the ankle joint and the Achilles tendon attached to the heel at point P. So I have a tendon here that's been attached to this point P. The tendon exerts a force of magnitude 790 newtons, as figure B indicates. So I have a F of 790 up. Okay, this F is 790 newtons. Determine the torque, magnitude, and direction of this force about the ankle joint. So in other words, I have a 55 degrees here, and this point is the ankle joint. Okay, so because we were looking about the ankle joint, so this is the axis of rotation for us. And then we have this distance here. Okay, we have this distance. So let's talk about our formula. Torque is R cross F. Okay, so in other words, torque is the amount of R, the amount of F, and the amount of sine of the angle between them. And let's see what we have. Okay, so the force is 790. So tau is RF sine. Force is 790. Okay. The R is the distance between the force. The R is the distance from the force to the axis of rotation, which is right there. And it's been given to us, 3.6 times 10 to the negative 2. So 3.6 times 10 to the negative 2, okay, times the sine of the angle between the force and the R. So that's the sine of some angle. So let's take a look. We have a triangle here. This is 55. This is 90 degrees. And this is our theta. Okay, so theta is 90 minus 55, right? Which is 35 degrees. So I have tau of 3.6 times 10 to the negative 2 times 790 times the sine of 35 degrees. Whatever it is, just put it in your calculator to find the value for it. Now let's talk about the direction. You have R cross F. So let's see what we have. You have R, which is this vector, and then you have F, which is, without changing the direction and magnitude of it, I can just point it right there. That's your F, 790. Okay, and that's the angle. And then what you want to do is to find the direction. So put your 4 fingers across a long R, bend it towards F. Your thumb will show the direction of the torque, which is inside the plate, which is inside your screen. Okay, so this will be towards the center. So tau will be to the screen. Okay, or to the center. All right, so a side note on that is this. When we're talking about the angle between the force and R, okay, or the force with the distance of the force to the axis of rotation, we're usually talking about the smallest angle. So in our case, if this is our force here, okay, then when I showed it here, I consider this to be the angle between them, okay, which is 145. So in other words, alpha is 145 degrees. Theta is 35 degrees. But the sine of theta and the sine of alpha is the same. They're equal. I think it's 0.57 degrees or something like that. So 0.57 value. So that's why we usually consider the smallest angle between two. Example number 3. So a diving board. A woman whose weight is 530 newtons. So we know what the mg is. That's mg. 530 newtons is posed at the right end of the diving board with length of 3.9 meters. So the total length is 3.9 meters as indicated right here. Okay, so this woman has a 530 newtons of weight down. So this is our mg. The board has negligible weight and is supported by a fulcrum 1.4 meters away from the left end. So that's where the fulcrum is, and it's 1.4 meters away. Find the force that the bolt and the fulcrum exert on the board. Okay, so in other words, find F1 and F2. We don't know what they are, but we know if this is at equilibrium, then all the torques should cancel out. Okay, and we are free to choose the axis of rotation to our benefit, because we can choose the axis of rotation to be able to solve the problem easier. So first, I'm going to choose the axis of rotation right there. Okay, so if axis of rotation is right there, then what we have is that we have a total torque of torque 1 plus torque 2 to be 0. So torque 1 is a torque because of this mg. So I have R1 cross F1, okay, and then I have R1 W, and then sine of the angle between R and F, which is sine of 90 degrees. Okay, so this guy is 1, sine of 90 is 1, and then you are left with R1, which is 3.9 meters away, times W, which is 530 newtons. Okay, and this is meters. So tau1, tau torque caused by this force of mg, or this W, is 3.9 times 530. Okay, and if I put that on my calculator, let's actually see what I'm gonna get. So I got this value, 2067. Okay, so that's the value for tau1. And let's see if it's positive or negative. Which direction is that? Is that causing a clockwise or counterclockwise? So this is causing a clockwise motion. Let's get T2, tau2 as well. So tau2 is R2 times F2, okay, which is R2, F2, and sine of the angle between them, which is sine of 90 degrees. And we know the sine of 90 is just 1. So R2 is 1.4, and F2 is unknown, okay? But I know that, and this is counterclockwise. because this will causing this type of motion, this will causing this type of motion. So I know their value should be, if I add them up, I know that the value should be 0. In other words, they have to have equal amounts, one counterclockwise, the other one is clockwise, so they have to have one is positive, the other one negative. So in other words, tau 1 value should be equal to tau 2 value, but they are having opposite direction. One is counterclockwise, the other one is clockwise, okay? So the counterclockwise is positive, the clockwise is negative, but they have the same value. In other words, 1.4 F2 should be equal to 2067. So F2 is 2067 over 1.4. Okay? Now, let's see. So we had this freedom to choose the axis of rotation, and we choose it right there. Okay, let's actually consider it to be located at the point of a fulcrum. Okay, so let's consider the axis of rotation to be right here. So that is the axis of rotation right now. So I have a W of 530, and we know what the length we have. We have 3.9 here, and we have 1.4 here, isn't it? 1.4, yes. So, and that's the axis of rotation, and then we have an F being applied down right there. So we know that all the torques should cancel out. Torque 1 plus torque 2 should cancel out. We have two forces. So torque 1 is R cross F. Okay, R1 and F1. So R1 is 1.4. F1 is F1, which we don't know what it is. F1, 1.4 times F1 times the angle between them, which is sine of 90 degrees, which is 1 all the time. So I have 1.4. Did we do the same thing here, or didn't we? Yeah, but that's correct. So 1.4 F1. Okay, now torque 2 is R2 cross F2. Okay, R2, now this is R2. All right, so that's R2, which is 3.9 minus 1.4 times F2, which is 530, times the sine of the angle between them, which is sine of 90. This guy is always 1. So torque 1 and torque 2, one would be positive, the other one would be negative. And it's really easy to choose one direction to be positive. So 1.4 is causing, which is coming from this F1, is causing this object to move counterclockwise. So this is counterclockwise, which we consider being positive. And this one will cause the motion to be clockwise, which is negative. Okay, so tau 1 should have the same value as tau 2, but they are in the opposite directions. So you have 3.9 minus 1.4 times 530 being equal to 1.4 F1. So in other words, if you want to find F1, you have 3.9 minus 1.4 times 530 over 1.4. And that would be the value for F1 here, okay? Which is this one. So we found both of them. We found both cases. Angular momentum. So it is analogous to linear momentum, P. If you remember, the P was mv, or mass times the velocity. But it is the linear momentum, or L, is pretty much the same concept. So instead of having m, I have I, moment of inertia. Instead of velocity, I have angular velocity, or omega. Instead of p, which is linear momentum, I have L, which is angular momentum. So the angular momentum L of a body rotating about the fixed axis is the product of a body's moment of inertia, which is I, and its angular velocity, which is omega, with respect to the axis. So that is the definition, and they are pretty much the same if you're looking at this. They are pretty much the same. So you have P equals mv and L equals I omega. Instead of, in a rotating object, instead of m, I have moment of inertia, okay, which is not only related to mass, but also how these little objects are configured, okay? And then instead of having a linear velocity, I have angular velocity because the object is rotating, okay? So angular momentum and torque, just like an object moving in a straight line has a momentum, an object moving in a circle has a momentum as well, okay? And the P and L are related. So remember, P was mv and L was I omega, okay? They are related. In other words, L is R cross P, okay? So R cross P is mv, which is mRV sine of theta, or the sine of the angle between R and velocity, okay? So this is very important. I am going to highlight it for you. All right, so here we go. So the rate of the change of the angular momentum of the particle equal to the torque of the net force acting on it. One more time, the rate of the change of the angular momentum of the particle equals to the torque of the net force acting on it. We have had the same thing for the linear. Remember, F was delta P over delta T. And remember that delta P was F delta T, which we call it impulse, or I. It's the same concept. These two are the same. Tau is delta L over delta T, or tau is dl over dt. The reason that we didn't use delta, this could apply to a very short period of time as well. This is for a longer period of time, okay? But it means that the torque is the change of the angular momentum over the change of time, and there is a change in the angular momentum over the time of that changed. In other words, if there is no net torque, okay, or the net torque is being 0, then delta L should be 0, and then that means L1 should be equal to L2, or L initial should be equal to L final. So the initial angular momentum should be equal to final angular momentum. So angular momentum initially should be equal to angular momentum finally. Okay, so delta L should be 0. If the net torque is 0. Okay, it's the same concept we had. If there is no net force acting on the system, then it's linear momentum, its momentum should not change. In other words, if F is 0, delta P is 0, and P1 and P2 will be equal. Well, we had the same concept. We have the same, we work on different problems for collision, if you remember, from previous chapter, chapter 10. So since there is no external force, okay, then if the external force is 0, in other words, then the momentum should not change. So if I want to write down what I just told you, I would say that external torque is delta L over delta T, or dL over dt. And this is for rotation. For linear type of motion, we have delta P over delta T, or dP over dt. Okay? So, angular momentum and velocity. The angular momentum of a rigid body rotating about the symmetry axis, or the axis of symmetry, is parallel to the angular velocity and is given by L equals I omega. Okay? So, for any system of particles, we have the sigma tau is dL over dt. And if you want to find the total torque, then you have to add the torques up. For example, the total torque or external will be torque of particle 1 and particle 2, 3, and so on and so forth. So for a rigid body rotating about the z-axis, we have that. So, and this is also coming from the analogy we had with the linear type of motion, that sigma tau is I alpha. If you remember, sigma f was ma, Newton's second law. We talked about it in the previous couple of slides back. So let's take a look at this one. If as I said, if you curl your fingers, right hand rule, okay, and then your thumb will be the direction of the omega. Your if the rotation axis, that's where I'm pointing at. If the rotation axis is the axis of symmetry, then L would have the same direction as omega, either positive or negative. But if the rotation axis is not the symmetry or the axis of symmetry of the object, then L is not along the rotation axis. It will have a different direction with an angle of, like, for example, 15 degrees, 20 degrees. Okay? So let's consider a professor holding two objects and an arm length away from him. Okay? So let's say that this is the axis of rotation in our case. All right, so I have an axis of rotation here. Okay, in this case, so I have this as my length 1 or R1, and this has the same length R. Let's say that his hands are in the same length. So I have two R's, one object here, the length of R from the axis of rotation, the other object in the same length from the axis of rotation. So when a net external torque acting on a system of object, or a system is 0, the total angular momentum of the system is constant. Same thing that I just said. In other words, if you have tau of external is delta L over delta T, if the tau of external is 0, then delta L is 0. Or L1 should be equal to L2. We know what L is. L is I omega, okay? Omega is the angular velocity. I is the moment of inertia, okay? So L1 should be equal to L2. In other words, if you want to write it, your I1 omega 1 should be equal to I2 omega 2, okay? So if your I decreases, your omega should increase to keep it a constant number, okay? That is a constant number. All right, so if your I, or a moment of inertia, decreases, then your omega should increase. Let me actually change the color of these to indicate that how important this is. Okay, so, and we know what I is. I is mr squared. So if r is decreasing, then I is decreasing. In other words, when you are holding two objects in your hand in an arm length, and you are not interacting with anything else in the universe, so the net external torque on you is constant, or it's zero, and you are closing your arms, you are reducing this I. So this R is decreasing, and then I is decreasing, and omega should increase. So that's why you're moving faster, because the L should be constant. So you're reducing R, and thus your moment of inertia should reduce. If your moment of inertia is reducing or decreasing, then your omega should increase, because you have to have this. Because you have to have the same L, you have to have the same angular momentum, and angular momentum is I omega. So if I is decreasing, then omega should increase to compensate that in order to have a constant value, okay? So this is a constant value, okay? So now let's take a look at this problem, a satellite in the elliptical orbit. We have an artificial satellite is placed in the elliptical orbit about the Earth. Its point of closest approach is 8.37 times 10 to the 6 meters away from the center of the Earth. Okay, so in other words, this is the axis of the rotation, and this object, okay, which is a satellite, is at 8.37 times 10 to the 6 meters away when it is closest to Earth. And its point of greatest distance is this point, for example, which is 25 times 10 to the 6 meters away from the center of the Earth. Okay, so this is 2 points, point 1 and point 2. And that's the axis of rotation, which is the center of the Earth. Okay, so this is R1, and this is R2. Okay, the speed of a satellite at the closest approach, or perihelion in astronomy term, is 8,450 meters per second. So at this point, the velocity of V1 is 8,450 meters per second. Find the speed at the aphelion, or when it is really far away from us. So in other words, find V2. Okay, so we know that there is no external torque. So no torque of external is acting on the object, or the torque of external is 0. Okay, so if that's the case, we know that what the torque is, delta L over delta T. This means that delta L is 0, or L1 is equal to L2. Okay, we know what L is. L is I omega. So I1 omega 1 should be equal to I2 omega 2. Okay, I is mr squared. R squared for the particle. That's the moment of inertia for the particle moving around. So mr1 squared omega 1 should be equal to mr2 squared omega 2. Okay. Now, if you're looking at this, m can cancel out from both sides. So then I am left with r1 squared omega 1, r2 squared omega 2. And v is r omega. Okay, that's what v is. And so omega is v over r, so I can just, or velocity over r. Okay, so the reason that I say this, because the velocity is given to us, 8,450 meters per second. Okay, so in other words, I can use this right here and right here. Okay, so I have r1 squared. All right, instead of omega, I'm going to use v over r. I have v1 over r1 being equal to r2 squared v2 over r2. So this r1 and this r1 squared will cancel. This r2 and this r2 squared will cancel. So what I have here is r1 v1 equal to r2 v2. Okay. So if you want to find v2, which is at this point, would be equal to r1 v1 over r2. So you have the values for both of them. So all you need to do is to substitute the values for all of these, for r1, r2, and v1, and you can find a value for v2 using that. So let's take a look at another example. Our sun's death. So when our sun runs out of fuel, and so the sun is turning hydrogen to helium in an event called nuclear fusion. And when all of if this process is done, then it will eventually become a white dwarf. And it's about the same size and the same radius as the Earth. So 6,380 kilometers is the radius, okay, of the sun at that point. Estimated the sun's rotational period when this is that size, okay? So we're looking for rotational period, or tau. And if in that case, the sun's current radius is about 700,000 kilometers. So its current is 700,000, or I'm just going to call it 7 times 10 to the power of 5 kilometers. Okay. And its current period of rotation is roughly 2.6 times 10 to the power of 6 seconds. So let's call one of them 1, the other one 2. Let's call this one 1 and this one 2 to be able to work on the problem. Okay. So let's work on it. What are we looking for? We're looking for tau 1. Okay. So we know that there is no external torque acting on this. So since the torque of external is 0, then I can say that there is no change in angular momentum, or delta L is 0. In other words, L1 should be equal to L2. So we know L is I omega, and so I omega 1 should be equal to I omega 2. Okay, so I1, and we know what omega is. Omega is 2 pi over tau, or 2 pi over t. So let me go ahead and make some changes here, because I don't want you to be confused. So let me go ahead and use t, or capital T, for period. So you're not confused then. Okay, now coming back, T1 and T2 for period. So I1 is I1, omega 1 is 2 pi over T1, I2 is I2, and omega 2 is 2 pi over T2, okay? Now, we know what I is for a solid sphere, okay? So I for solid sphere is 2 over 5 mr squared. That's what the I is for a solid sphere. It's not given here, but it's usually given in the problems. We don't want you to drive it or to find it. So if it's necessary, we'll give this to you. I just have it in my mind because I've worked with these problems for so many years. So 2 over 5 mr squared. So now I have to put this in our equation. So I have 2 over 5 m r, which is the radius, 2 over 5 m r1 squared. That's what I have right there as I. 2 pi over T1 being equal to 2 over 5 m r2 squared 2 pi T2. So when you're looking at this, this will cancel out with this. So 2 over 5 and 2 over 5 will cancel out. M and M will cancel out. 2 pi and 2 pi will cancel out. You are left with R1 squared over T1 and R2 squared over T2. So if you're looking for T2 or T1, so T1 then is T2 times R2 over R1 squared. Okay, yeah, that's correct. So T1 is T2, which is 2.6 times 10 to the 6, 2.6 times 10 to the 6 seconds, and then R2, which is 7 times 10 to the 5, kilometers over 6,380 kilometers. So whatever it is, and it will be much faster, will be your period or the sun's period after it runs out of a fuel and turned to a white dwarf. So a tangential force applied to a rigid body does work. We're going to talk about the rotational motion, work on the rotational motion. So a tangential force, or F of t, applied to a rigid body will actually do some work for us, okay? Similar to the linear motion. So the linear motion work was F dot D, if you remember, or F d cosine of theta, force times the displacement times the angle between, cosine of the angle between them. So in our case, since we are rotating, the work done in the rotational motion, instead of force, I have torque. Instead of displacement, the linear displacement, I have angular displacement, which is delta theta. Okay, and this cosine is always the cosine of 90, cosine of 0, which is always 1. So I have tau times delta t, delta theta. And the work energy theorem is still holds for the rotation. So the total work, okay, or work of total, is delta k, which is k2 minus k1, k of final minus k of initial. K of final is half I omega 2 minus half I omega 1 squared. So half I omega squared minus half I omega squared. Now, if that's the case, if i's are the same, let's say that m or r does not change, so this I and this I the same, is omega 2 squared minus omega 1 squared, okay? So, and these are i's, and just don't mistake them with 1 or anything else. I wrote it a little bit weird when I wrote fast. So I have I right there. So it's the same thing. So if you have a rotational type of motion, the force applied will do work, and that work, instead of having a linear type of relation, it will have a rotational type of relation. So instead of force, I have torque, and instead of displacement, linear displacement, I have angular displacement, which is delta theta. And then the total work will still have be equal to K2 minus K1. So total kinetic energy final minus total kinetic energy initial, which is half I omega squared. Power in the rotational motion. The total work done on a body by a torque is equal to the change in the rotational kinetic energy of a body, and the power due to that is tau times omega. It's the same thing that we have had before. And the previous relation that we had for power, which was work done on an object divided by or over the time that that work was done, will give you the power. Or here is joule per second, which we call it watts. It is still the same relation. It does not matter what you're talking about. If you calculate work, and if you calculate the time that that work was done, if you divide them, you'll get the power, which was in terms of watts. Okay, but the power due to a torque will also have this type of relation as well. So let's talk about summary of chapter 11. You have 3 slides that are very important. A force applied so as a cause of angular acceleration is said to exert a torque. Torque due to a tangential force, or tau, is R times F. If you want to look at a more general format, you have to look at it this way. Tau is a vector, is R cross F. They are both vectors. And basically you're saying multiply the magnitude of R, magnitude of F, and the sine of the angle between them. And if you want to write the Newton's second law was sigma F equals ma. Now you have sigma tau equals I alpha. Instead of m, I have moment of inertia I. Instead of a, which is the linear acceleration, I have alpha, which is the angular acceleration. Okay? And then in order for an object to be in a static equilibrium, the total force and a total torque, so not only force but also total torque acting on the object, must be 0. An object balance when it is supported in its center of mass. So in systems with both rotational and linear motion, both of them are presented. Okay, for example, a bus wheel is rotating, or you have a sphere that is going moving from point 1 to point 2, but it's also rotating at the same time. Okay, so rotation without it's rotating, but it's not slipping. So Newton's second law must be applied separately to each. So in other words, you have to have F equals ma for translational motion, and you have to have tau equals I alpha for rotation. Angular momentum, it's very similar to the angular momentum formula that we had before. So the angular momentum formula that we had was mv, and now it's I alpha. The tangential motion, in a tangential type of motion, and also we have L is R cross P, right? In other words, L is RP sine of the angle between them. So that's your L. And then L, so that's your L. And then L is R, P is MV, sine alpha. okay, or sine theta, which is the angle between them. And then Newton's second law was telling us that F is delta P over delta T for the linear type of motion. And then for rotation, I have delta L over delta T. So if no force is acting on the object, so if F external is 0, then delta P is 0, or we have the conservation of linear momentum. And then if tau of external is 0, then we have the delta L equals 0, or we have the conservation of linear momentum. Okay. So if the system has no external torque, the angular momentum is conserved. The work done by a torque is force, or torque, times the displacement. And displacement is in angular displacement, which is delta theta. So if you remember from our previous formula for work was F dot D, okay, or F d cosine of theta. But here, instead of F, I have torque. Instead of displacement, linear displacement, I have angular displacement, delta theta. And the power is just F times V, if you remember. Because if you remember, the power was work done on an object divided by the time that that work was done. And then the work was F d cosine theta, right? F d cosine theta. And T was T. Now what you have is D over T, displacement over the time of that displacement, which is velocity. Okay, so now you have F V cosine of theta, which you can easily write it as power being equal to F dot V. Okay, that's also true. Rotational quantities are vectors that point along the axis of rotation with the direction given by the right-hand rule. Okay, so if you have two vectors, for example, vector A being multiplied by vector B in a cross product, A cross B, and let's say they are equal to C, which is another vector, they have this type of relation to one another. That's A, then that's B, and then this is your vector C. Okay, this is a 90-degree angle. This is also a 90-degree angle. And let me actually go ahead and change A and B because this is more accurate. A cross B is equal to C. So you have to have your four fingers along the direction of A, bend them or curl them towards B, and then your thumb will show the direction of C. If you're making a cross product out of them, A cross B equals C. Okay, like for example, L is R cross P, two vectors. R cross P is L. A cross B is C. They are vectors, okay? So have that in mind for finding the direction of these stuff using the right-hand rule. Right-hand rule. All right, this is the end of part 2. If you have any questions, let me know.